Good morning, everyone. So let's just have a look on. So till to date, we have studied the free vibration, damped, undamped, forced vibration. Damped means forced vibration, damped also. And in that case, we have also seen different types of forcing functions. That what are the different forces function we can take, and how we can able to solve that. In the last lecture, we have introduced the Duhamel integral, and with the Duhamel integral, we have used the D operator, and with the D operator we have seen that different type of forcing function can easily be considered with that. So we have shown like the three different cases here, like that mostly that 3 or 4 different types of forcing function can be possible. So one is the f equal to e to the power I omega t type function, which is exponential function. So we have seen that how to solve the exponential function. So we can just substitute d equal to whatever the e to the power omega t are there, so that e to the power omega we can substitute. Then the second thing is comes sine or cosine type function. So in sine or cosine type function, we can substitute d square equal to minus omega square. That we can substitute, but remember you cannot substitute for d. So once you are substituting something, then if the d is there in the denominator, then you have to multiply with the complementary part of it, so that you can rationalize the function. So the top part d will come, and the bottom there will be no d. So there will be d square, and then d square you will substitute again minus omega square, and we can get the solution. Then next thing comes constant. So constant case, you can assume it constant some value into e to the power 0 into t. So then you can substitute instead of omega, that will be 0. So again you can write accordingly. Then third case comes polynomial of t. So polynomial of t was little bit tricky. So we have done that full polynomial of t. How to do that? So like first we can express this term as the middle term factor. So whatever the d square minus 2 xi omega d plus omega square, that thing we can express as the middle term factor like this way. Then we can rationalize this portion as the 1 by something minus 1 by something. Then we do the binomial expansion of that. So from there we can actually take the d at the numerator. And if we see once we are doing this type of binomial expansion, always the question comes, what are the up to what term we have to take the integration, up to what term we have to consider. So in this case the simple answer is that until and unless your terms are get exhausted. For example, if you are doing for t to the power 5, then d to the power then d6, like a sixth order derivative will gives you 0. So you should do up to d5, that will give the constant value 1. And as you remember that this step was mistake, so you should not do like this way. You should better do from the very first step, one after another you should do, so that it can be solved. Okay, don't just jump it from the first, so then it will give some erroneous result. Then we have checked, like suppose if the forcing functions are not throughoutly same, they are changing with some time span, how to consider that. So there we have done that, like suppose for example there is an increasing force, a decreasing force, like we have applied some force, goes up and go down. Then first we can, so we have to divide the full time domain into those steps. So first, like once it is increasing, we consider the increasing force condition, we put that increasing force condition and we solve it. Then again it is getting decreased, so we do it, and then it's a free vibration once there is no force applied on that. And in all those cases it is advisable to change the coordinate. Like for example, once we are solving this portion, it is better to use tau 1, where the tau 1 is something equal to t minus t0, where the force is changed, so that you can able to solve it and use the previous condition where the solution is ending, that as the initial condition for this step, and you can solve that. Then next thing we have just introduced, that is the Duhamel integral. So in the Duhamel integral, like suppose once we are applying an impulse force on the structure, then how it going to like oscillate. So we have seen that impulse force is a instantaneous process. So once it is instantaneous process, and impulse is associated with the change of the momentum. So change of momentum means, so that we can say that if the impulse force amount is I and mass is m, so change of momentum, or the change of velocity will be I divided by m. So once you are implementing the impulse force on that, so impulse divided by mass is equal to your change of velocity. Now if we assuming that the velocity was 0, then change of velocity will be I by m. So we can say that the initial velocity after having the impulse, because impulse is instantaneous process, so we are not considering that any time between like impulse started and impulse finish. So it is like x0 equal to I by m. So we have the solutions, we know what is our solution, we can just put that and we can get, this is my solution of the time. Okay, so that up to this stage we have done in the last class. Okay, so today we will start from here, that what are the things coming. Okay, so in the Duhamel integral, so if you see, we have mx double dot plus cx dot plus kx, that is equal to your force. So whatever the forcing function it is, it hardly matter. So like for example, let's say we have some very random type of forcing function. Okay, so how we should start doing it? We are thinking that let's take a small strip of it like this. Think that is applying at the time t, this force is applied, or maybe you can just say at time tau. At time tau, this force is applied on that. Okay, and after that we are measuring the time. So this is my time. Okay, so once this impulse is applied, so what is the response of the structure? So response will be equal to x of t should be equal to how much? We did it in the last class. So if you see, e to the power of minus xi omega t x naught and now x naught dot was I by m. Okay, so what can I write? Can I write it? Please. Very good. If I can able to write that here, please tell me one thing. From where the t is started measuring? From where we are started measuring the t? Tau. So should we put t here or t minus tau? So how many of you think that t minus tau we should put? It should be t minus tau. Exactly. So that thing when applied at beginning. Now if we think force applied or impulse applied at t equal to tau, in that case what will be my response? T minus tau will be e to the power of minus xi omega t minus tau I divided by m omega d sine omega d t minus tau. Make sense? So that will become the expression. Now think that the response is, so you have that system, so once you are applied at tau time this impulse, this gives the response. So that tells that after you have applied this, how your graph will, so this is the basically a sine function maybe, so it will be like getting decayed. Okay, there is nothing but that, because it's not just sine function t minus omega tau. That means we are shifting the axis, not starting from 0, and we have this term, so that is acting like a magnitude of that, and e to the power xi omega t minus tau, so that's a exponentially decaying function. Done. So there are the three components of it. Make sense? Anybody has any doubt? This thing is like a magnitude of it, like where it will start, so that will be like I by m omega t. This is like a sinusoidal function, so this is basically a sine function, and this is a decaying function. So if I just add 3 of that, it will be showing a decay after t minus tau. All of you agree with me? Very good. Now think that we are not just solving for a single impulse. What is our objective? To solve for a complete force response. So what do we have to do? We have to integrate the full thing. Now, before doing the integration, we need to understand another important point. That is, suppose we have this response. Now, again you give another impulse after certain time. Okay, because that is exactly happening. Like suppose, for example, you have this thing. Then suppose if you take that next strip, then again it will give the response. Again next strip, again next strip, again next strip, like this way. All the responses are coming. So integration is possible provided you are allowed to do the superposition. So first we have to understand whether the superposition is allowed or not. If we see yes, it is allowed, no problem, we can do the superposition. So here if you think, what does the meaning of superposition? Exactly, adding the two responses, and we are anticipating that if we add the two responses, we should able to get the same response back. That is our thought process, and that's why we can able to add that up or not. Make sense? So think it in some sort of way. I mean, if we just take like one after another, that will be complicated. Just think. For example, we have a response and we have some impulse at some point. Then after a certain time, I have a impulse. Okay. That means like you have some structure, you just impulse it at certain point, let it go, suddenly again impact it. Okay. What is happening? So if I try to see that this type of case, how the plot should look like? First there will be no response. Suddenly at this point your velocity will actually jump, displacement will not jump, so it will coming like this way. Something will happen for the first one, and second one also you will see it will start like this, and if you see the impulse will actually looks like it will go getting decayed and suddenly again it will jump. So that way it will happening, because once you will have again another impact, it will again jump. So whichever is going to decay, that again is rejuvenated due to the next level of impulse. And it can be seen that this superposition actually holds good if the system is linear properly. Then we can able to use this type of thing. Not a problem at all. So here also the system is linear, all those things are okay. So we can able to use that. And that is the fundamental of the Duhamel integral, and sometimes this is also known as the Green's function operator, because it is calculating at a particular point. We are solving the response for a particular time instant, and then we are integrating it over the domain so that we can able to get the complete response of the system. Make sense? Okay, so my total response will, so here this thing, once we are doing the integration, I can write it as the del x. Okay, so that will be del x will be e to the power of minus I omega t minus tau I by m omega d into sine omega d into t minus tau into t tau. So x will be integral 0 to t e to the power of minus I omega t minus tau into I will be f of tau. Simple, because at that point whatever is the force, f of tau into sine omega d t minus tau d tau, and we can take m by omega d out, because m by omega d is the constant number. Omega d is the damped natural frequency of the system, so that will depend on the system, not on the force, and mass is the mass of the system. So both the things are the system property and can come out, they are not changing. Okay, and so we can able to get the response like this one. Any doubt up to that? Clear? Fantastic. So now you can think, so this is my solution came here, so you have to perform the integration and you can able to do that nicely. It should able to give that. One thing, please remember that once you are doing the integration, you have to so there are two terms, one is t and another is tau. With whom, on what term will you do the integration? Which will be the which is the varying parameter, t or tau? Tau. Very good. So then what is the value of t? Can you little bit explain, like how we are exactly telling range of tau? Think how it is exactly. So my response is x of t, that is equal to 1 by m omega d integral 0 to t f of tau e to the power of minus xi omega t minus tau into sine omega d t minus tau d tau. So so if I just try to see all the numbers, m systems mass, omega d is the damped natural frequency of the system, fine, we have no problem. F tau is the response, like if we are going the tau, varying the tau, so whatever the value of f tau is coming, that f tau we are taking, so that is from the forcing function we can able to get that. Next thing comes xi. Xi is also the damping of the system. Omega is the natural frequency of the system, that is also fine, and here omega d also the damped natural frequency of the system. So the problematic thing is the t and tau. What is t and what is tau? Because that is important point to understand, otherwise it will be very crazy. So one of you actually suggested that t is the range of the tau. That is not wrong. I mean, suppose if you see, that is my time axis, so t is the overall time axis and tau is like a where we are doing the integration. So that point is the tau. So that tau, so suppose we need to estimate the response at this point. So this point will be my t, because we try to estimate the response at that point. So that point will be my t. Okay, agreed? And tau will vary from here to here. Make sense? That is why if you see that integration is happening on terms of tau, and t is the limit from 0 to tau, means the 0 to t, the integration is happening. So that is the tau is varying. Okay. And you can think that you need the response for different time, because your response is not a single value, it is a time history. So there you will change the value of t. Got that point? So you will get the response throughout. So suppose you need the response at t1. Let's say this is t1. Maybe I just mark it with the red color. Maybe you see this is the t1 point, this is t2 point, this is t3 point. So once you are doing x of t1, then you will do it m omega d in 0 to t1, then full integration. I'm not writing the full integration, it will be remain same. And just only thing is that you will put t1 minus t. That is the only thing. Maybe if I just call it that some constant a into 0 to t, maybe I just say that f of t minus tau d tau. So in that case I can easily write it a into f of t1 minus tau into d tau. Got that? Is that clear? Very good. And once we are doing for x2, again we will do it for 0 to 2 f of t2 minus tau d tau. Any doubt? Any doubt? Anybody? So here you can see the effect of t1 means the t is coming into picture. Okay. So how far you want to check? You can change the t accordingly. Now maybe you are thinking, my God, if I need to find the complete solution, so many integration I have to perform. So is it like that, or maybe not like this? Numerically, if you try to do that, it is the case, definitely. And numerically also you don't need to be worried that much. You will write a MATLAB code or whatever the code you want to write, like Python, MATLAB, whatever the language you are preferring, you can write that and you will make a loop. It will just calculate the full thing. So you do not need to do it by yourself. Or if you want to do it by integration manner, don't use t1, t2, t3, t4. Just use t. You will get an expression. And in that expression, you can substitute the value of t, whatever is coming. You can able to get the solution. But you have always, there is a but, that what is your f of t, tau? Do you really have an expression for f of tau or not? If you have an expression of f of tau, fantastic. If you do not have an expression for f of tau, then you have to go for the numerical. No other choice. Like for example, earthquake. If you see, what type of earthquake data we generally get? Anybody? We have several persons who are in industry. Any idea how, what type of data we are getting for the earthquake? Once we are doing the time history, not the response spectrum. Huh? Intensity versus time. Intensity.
PGA?
No, not PGA. Acceleration versus time. Okay, don't say PGA. PGA is one of the specific value of acceleration. Okay, just acceleration versus time we are getting. Generally, these are recorded in 0.01 0.02 second interval. Means some station maybe it is recorded 0.02, some station may be recorded 0.01. Okay, so we get some data set. More or less, standard earthquake records, if you see, comes around 40 seconds. And mostly if it is measured by 0.01 second, so you will have a 4000 data point. So the total response can be calculated like this way. So total response of the system will be e to the power of minus xi omega t into x0 cos of omega dt plus x0 dot by omega d sine of omega dt plus 1 by m omega d integral 0 to t f of tau into e to the power of minus xi omega t minus tau into sine omega d t minus tau d tau. That is the total response of the structure. Very simple. If you see, this portion we already understood, and this is that part. And what is the first part? First part is the complementary solution of the system. Okay. So generally the structural dynamics things is easy if you just try to see that how it is. Okay. Sometimes like we feel quite afraid by seeing that complicated equations, but try to see the parts of that, then it will be quite easy. So this is nothing but the complementary part of the solution, because you have to add the complementary part now, because once if you are started the solution with some initial condition, that will also stay, as well as you are having the forced. So this thing gives the transient vibration. So complementary, that's the transient vibration will come, and this is the forced vibration. But here the forced vibration is not a harmonic forced. Therefore, your forced vibration part is quite complicated. It is not just only the XP. That XP looks like this, that particular part. Okay. So theory remains same, that complementary plus particular, but particular becomes this type of complicated thing. And it is calculated like that all procedures. Okay. So just let's quickly see one small example so that we can able to do that. So let's the mass M. So mass is equal to, let's say 100 kg. Stiffness equal to 10 kilonewton per meter. It is at rest, and we are applying a constant force of 1 kilonewton for 1 second. Okay, so how to do that? Simple. So if you see, so first case, like maybe assume there is no damping. Okay, so we don't have damping. So how the things will happening? So my equation was x of t, that will be equal to, so here x0 equal to 0, x not 0 is also equal to 0. So that first transient part will be no longer there. Okay. So whatever was there, like it was xi omega t into x0 cos omega dt plus x not 0 by omega sine omega dt. That part will no longer there, because this is 0, this is 0. Done. Plus we will have 1 by m omega d integral 0 to t f of tau into e to the power of minus xi omega t minus tau d tau, not d tau, into sine omega t into t minus tau d tau. Okay, now you can see that xi is equal to 0. So this part has become 1. So you left with x of t equal to 1 by m omega d integral 0 to tau. F tau is a constant value, so maybe I just put it 1 kilonewton, so it's 1. So you just left with sine omega d t minus tau d tau. That is simple. You can do the integration very quickly and get the solution. So if you do the integration of that, you will get, or maybe if I just put that f is constant, so f0 is here. So f0 divided by m omega t minus cos omega d, so that will be omega d square cos omega d into t minus tau 0 to tau equal to 0 to t. Okay, that we can get. Now you can see that as xi is equal to 0, omega will be equal to omega t. So what can I say? f0 by m omega square into, now if I, and also that t is equal to 1 because it is applicable for the 1 second. No, not t equal to 1, yeah, so it's just go for 1 second. So if I just substituting it, so cos of omega into t minus 0 minus, so it will become plus cos of omega into t minus t. So f0 divided by m omega square into cos of omega t will become cos 0. So that will be cos of omega into 0 minus cos of omega t. So f0 divided by m omega square into 1 minus cos omega t. So that will become the response of that system. Get the point? Now we have to think one point, that if we are changing the force instead of a constant value, if you are making it like a exponential or something, then you have to perform the integration by parts, because then it will have like a two terms. So suppose for example, if you think instead of that f0 go out, if you have that is also a function of t, then you will have like this type of condition here, and you can only able to solve it if you do the integration by parts. Okay, now if the damping is also there, life will getting complicated. so those things are very difficult to do it literally. There are so many tools like MATLAB and all those things, you can able to put that and you can able to get the full expression also. Okay, just I try to show that, okay, how the complexity can be increased. Okay, but your t is going here, so this is somewhat like t1. Okay, so if t is less than t1, you can get this done. If t is more than t, if t is greater than t1, then what do you have to do? You will solve up to this, fine. After that portion, you have to solve assuming a free vibration, because there is no force. So whatever the response is happening at that point, you can calculate like this. You can identify what is the like a velocity and displacement coming at t equal to 1 and use that as the initial condition for the rest of the problem, because that's a free vibration. We will do that in MATLAB. We will do that type of like 2-3 problem we will solve, so that only for that this to this person. Exactly. So after that, this is a free vibration problem, no force are there. So whatever the condition, like a final condition is coming, like x and x naught, whatever is coming there, x and x dot, so that will act as the initial condition and then we have to solve. So simply you can also see like this way, that we can put x equal to t equal to 1. So you can calculate f0 m omega square 1 minus cos omega. So that will be my displacement at this point. And you can also calculate what will be the velocity. X dot t will be f0 by m omega square, 1 will go and cos will become sine omega t, that will be 1 by, so this will be cube. Okay. So now here also if you put that 1, that will be f by m omega cube into sine omega. Okay, so that too now will become your initial condition, and then you will solve for the rest of the thing. We will come in the numerator, right? Perfect, yes, you are right, that will be omega only. I will come on the numerator. Perfect, yeah. So this will become your initial condition, and you will solve the problem, rest of the problem for this initial condition, assuming that it's a free vibration. Does that make sense? Keep on vibrating, exactly. Because no damping are there. And if you are putting that damping, you will have, like here maybe you will have that damping term e to the power of minus by omega t minus tau. You have to do that with the integration by parts, solve it, and from there you can get that solution, not a problem. So you can see that the TS have made the code for the dual integration. So this is for the, oh, exactly what I showed. So you can use those parameters. Yeah, so here the damped portion is here included. So just let me run it. This is live editor. So you can see, let's see what are the things. So T1, like time till which the force is acting, is going up to 10 seconds. F0 is the force magnitude of the constant force, omega equal to 1, and excitation frequency, and then K is the stiffness, M is the mass, so and eta is the damping is coming there. So then NF, so NF is the like a natural frequency is calculated, omega damped omega means omega d is also calculated there. Then x0 is the initial condition. So initial condition you can notice 0.01 and velocity was 0. So 0.01 was the initial condition. So it will be starting somewhere here. Yeah. Then it goes up because you have a forced vibration. So it goes up. We have also seen in the last class that how the only forced vibration will work. It goes up and then we leave it. So here you can see that once we leave that force, now it start oscillating over the 0.0 because it get displaced, because in that constant force problem also it went up and then take some time to settle and then settled because the force was there. Now you think force gone, so what happened? It has a displacement. So displacement amount was f0 by k primarily, because if you have a damping, then basically your displacement will be equal to the force by stiffness. Simple, because it will go come back, and it will stay at the f0 by k. So it will do like this way, same manner. You can also cross check that it is somewhat in the one range it is coming. So you have a stiffness of 1000 and force is how much? Force is also 1000. So 1000 by 1001. So you can see that they are more or less settling, try to settle down at the 1. But what happens? Suddenly you release the force. So again it start oscillating because it has a displacement up to 1. again it goes, so again it come back and starts the free vibration. So this portion is the forced vibration part. After that it is a free vibration part. Is that clear to all of you? Not clear?
Yes.
Perfect. Any doubt from anyone? Please feel free. Okay, very good. Then we did like one problem, that is a ramped with force vibration. So ramped with a constant force. So ramp and then a constant force. Okay, like we are not increasing the force directly, but it is slowly increased, goes to a particular value, and then it remains constant. In that case, how it will happen? So your mass is 10, stiffness is 1000, natural frequency you can calculate, zeta you can calculate, all those things. Then yes, so here you can see that some of the things we have to do. What I was telling, that you have to identify what time you solve. So you have to give a condition, like if else condition is coming here, that if t is less than td, then the solution is one type of solution, and if the t is more than dt, which is the else condition basically, then you will solve like this way. So your solution is coming, like you can see that it goes up to a particular point. And also you can see, if you have a only static problem, you will see it will increase in a straight line, because force versus displacement, stiffness will be your displacement. Stiffness is constant, force versus constant value, force is also a constant value, increasing, so it will increase like a linearly. But here you see it is not increasing linearly, rather it is changing, and it go at that point. Then what happens? Now you make the force constant. So if you think in our way, you will put it from t equal to this value 0 to t1. Your f of t is equal to t, let's say, increasing value. Then you make it constant. So now after t1, means once t is greater than t1, your f become f0. So it become a constant value. So you see, again it try to oscillate and try to come in that range. Make sense? Any doubt? We can also change the values and also play with it, because codes are ready, so you can just put the values and you can change. Then triangular force. Triangular force is like using non-one. Triangular one you have to do. Okay, so enter the stiffness, maybe let's say assume 10, 100, mass in kg maybe 1, coefficient 0.1, initial displacement maybe 0.1, this is also 0.1, velocity maybe just 2.01, peak force amplitude 10, very good. Very good. So the first one is my forcing function, how the forcing function is varying. So you see that we are applying the increasing force. It's a triangular force, so obviously it will increase, reach to a certain value, again decrease, and then it vanishes. We are not applying the force. So what happening? Once we apply the force, and we have also given some boundary conditions, so displacement, some initial conditions, so we have some displacement, some velocities. So it will start from that point, it will go and some oscillations are happening, although we can see much more oscillation if we reduce the time period of the structure, or forcing frequency of the structure if we can, not forcing frequency, because here forcing frequency is not there, it's just a force. So if we reduce the natural frequency of the structure, maybe we can see much lines, because these are dominated by the transient frequencies, because still the structure is not reached to any particular point. So these are mostly the transient part. And then again it is showing coming here, and then you see after that too your response has become like a completely, it's a like a constant response, but there is a slight decay due to the damping, but damping maybe amount is very small, that's why this small decay is happening. Means if you see very small, very light damping, you can see. So like here if you see this touch this line, here it just up this line, but it's very small, very minute. I can try to increase the damping and let's see. So this is like as good as the undamped case. So previously I put the initial damping coefficient, I put 0.1, maybe I should put it somewhat like 1 or something. Chalo, let's see. 100, 1, damping coefficient, put it 1, initial displacement, I can put it 0 also. Now so 0, 0, force 10. Huh? Okay. 20. This time graph is quite changed. It's somewhat high damping. So you see now the curves can be more traceable. You see that like if you see that in this portion the curves getting increased, it reached to that point, then again it is getting decreased, come here, and here it start oscillating and it's slowly decaying. So this way you have to basically solve. When the forces are changing, you have to change your functions, integrations, all those things you have to change, and you have to get the solutions for those portions and then add them up. Very important point. How you can check that all the things you have done correctly. This graph should not be discontinuous. It should be continuous, because you are supposed to use the previous state end condition as the initial condition of your next step. Obviously, when structure is vibrating, so it cannot just have a sudden displacement or sudden jump in the velocity. That's not possible. It's possible if it's subjected to some impact. But yeah, like for time being, but that is also okay. Means you know there is an impact. So and you also know that where the change you can able to see. You will not change the discontinuity in the displacement. You can able to see the discontinuity in the velocity. Velocity will be changed, because suppose if something is getting time impacted, then the velocity is flipped with the coefficient of distribution. Means whatever the impact it is happening, like suppose it hit 1, coefficient of distribution is 0.5, so positive 1 will become minus 0.5. So there you can see a jump in that discontinuity will be there, and you cannot able to calculate acceleration, because there will be jump in the displacement. So if you do the derivative, it will be not possible. You will not get any acceleration. So that thing happened, but these are like a much more deep into the structural dynamics thing. Like once the impact and all those types of responses are started coming.